I would love to be in Egypt. I couldn't make it this time. I hope next time. So as Roland said, I think these are transformative times for many disciplines. My name is Sotirios Kotsopoulos. I'm an associate professor at the School of Architecture at the National Technical University of Athens. My background is in design and computation. I received my PhD at MIT in 2005, and since then I did several research projects at MIT, and I still have a research affiliation with MIT. And Tina, would you like to introduce yourself, please?
Sure. Hi, I'm Tina Vartziotis. I am currently a PhD candidate at the National Technical University of Athens, working with Sotirios. My background is in mechanical engineering, and I did my first master's thesis at MIT with Roland Pelenka and Franz Ulm. And I kind of was impressed about all these urban physics topics. And right now, my research is mainly focusing on resilient cities and also how to connect urban mobility within this discipline as well, because I'm very passionate about the automotive industry, where I have also some experience, and we kind of want to combine these disciplines all together.
So the title of our talk is Using Open Data and Digital Photogrammetry to Capture Embodied Carbon Footprint and Urban Heat Islands. And the title itself, I think, well, first of all, it says a lot about the cross-disciplinarity of this type of approach that we are going to introduce. In fact, this is a collaboration of the National Technical University of Athens with the University of the Aegean, and you will understand why, because part of what we do is related to surveying older settlements and villages in the Aegean, but also the Massachusetts Institute of Technology, the Laboratory of Socio-Technical Media. What we are doing is basically, it has two pillars. One is collection of we do collect geo-referenced spatial data, extremely dense cloud points from actual urban environments or built environments with terrestrial and aerial means, and I'm going to explain what that means. Terrestrial means include cameras, laser scanners, etc., or portable scanners, and aerial means include drones, basically. We collect this information and we generate 3D models, extremely accurate, that can be used in precise calculation of embodied carbon emissions, in this embodied carbon footprint in this case, and heat island detection. Nonetheless, this information, these models can be used in various ways, and you know, we can use them in whatever ways we want. For this talk, we are only going to talk about embodied carbon footprint and heat island detection. The presentation follows pretty much the following steps. First, we expose the problems that we are attacking here and what is the motivation. We are going to give you an overview of the technologies of surveying, terrestrial and aerial, and then explain a little bit what is the surveying process, how we go and about to collect this information, and then talk a little bit about what the applications may be in embodied carbon footprint calculation and urban heat island detection. Finally, we're going to close with some thoughts about future steps and discussions about the process. Yes.
Yeah. So the two main problems that we want to not really solve, but approach and try to understand as much as possible and to relate them also to the city environment is the high temperatures in the city when compared to their environments, which has been a huge problem for most of the cities the last few years, and also the embodied carbon footprint, which actually arises almost 40% of the CO2 global emissions based on the building materials within the construction. So if you could go to the next page. Yeah, perfect. So, and the reason why these problems are kind of very important is that because we know, like, based on the predictions of the United Nations, that by 2045, the urban population is going to increase by 50%. And that means that cities and towns will expand, and the already existing problems will only magnify. And in this aspect, we have to kind of find ways how to mitigate the effect of the embodied carbon footprint or the urban heat island, and of course, much more problems within the city environment. Go to the next one. And in order to be able to do any of these things, one of the first big step is to be able to quantify cities and to model cities. And there are a few 3D models that can be used to model these cities. And actually, there's also another one, which is the city texture model that I was working on with Jake Roxon, Roland Blank, and Franz Ulm. And what it actually does, it models buildings as particles to quantify city parameters. This is one of the aspects which we want to be able to create models for the cities. But the other aspect that we are very interested in is to see what are the sustainability parameters that are related to the city environment and these city models.
Sorry, I forgot to turn on my mic. So as I started saying at the beginning, these are very transformative times for many things that we used to do in certain ways as new technologies are introduced, especially in urban planning and architecture, but also in building materials, as you very well know. There is a class of different ways, different technological means that we use. And we used to use in the past topography, tactile methods and on-site measuring of certain parameters, and especially in the urban fabric. That was a very tough thing to do with accuracy. Today, we introduce a new class of technologies, close-range photogrammetry and 3D laser scanning, drone and aerial photogrammetry, LiDAR, satellites, and remote sensing that make this surveying much more precise and much more easy. In particular, in our research, we use photogrammetry, close-range UAVs, drones, right, and terrestrial laser scanning, which is extremely accurate, and it's actually for the more limited areas. And all this is provides georeferenced data through GPS. We use this using these three technologies. We are able to produce accurate 3D models of the urban fabric or specific buildings that also are transferable to AR and VR if necessary. Or we can produce very accurate models in technical drawings with BIM or Revit or any other type of software we need. The steps are roughly the following. First is the digital surveying, a collection of data using these technologies that I mentioned earlier. Sometimes we use a combination, right, of these technologies, and it's not always a very clear process. So there is some planning that goes ahead, depending on what we are interested in. And then it's the processing of the survey data to produce the models. And then based on, the type of information that we want to deliver, we deliver the collected data and the models. We do a different type of processing, perhaps. For instance, if we want to have an AR or a VR experience, we take a different path, or we may take a different path if we are more interested in technical aspects. Maybe we can deliver beam models. And finally, a last step is to develop specifications and guidelines for our clients, so to say. These clients can be companies or can be cities, city officials, technical people for the city. And what we do in this case is we develop a specification, a protocol, so to say, that we deliver to them so that they can redo the same, they can follow the steps and revisit the same problem that they are trying to track with the same means that we use, but perhaps with their own personnel without hiring us. So a little bit of the technologies that we use. These are laser scanners. You see here laser scanners. These are the common laser scanners that, as you can tell, they can scan a limited area, right? They are extremely precise. And there is also a set of laser scanners that one may use that are hand portable. So they are much smaller and lighter, but they are used basically for details. These are the most common size scanners that we all use in the field. And then we have the area survey technologies that use photogrammetry. In this case, we have drones that, or portable cameras, or 360 very fine resolution cameras that can be used in different for different purposes, to survey, to capture exterior spaces or to capture interior spaces with high resolution photographs and large number of photographs. And I'm going to explain how that works. Basically, if you are familiar with digital photogrammetry, it works by taking multiple photos from different positions. So the camera is actually moving, right? We use, these are standard cameras that are take many photographs, which are georeferenced, and then with GPS, each one of them. So the other thing is that except from the motion that is required, so the camera is moving, right? So each point is captured from different positions. The other thing is that there is a 75% approximately overlapping between each photograph, so that we have multiple let's say, photographs and GPS associations for each one of those points, which allows us to insert them into appropriate software to determine the exact location from which these photographs were taken, and to calculate the three-dimensional object of the object, the model of the object. So basically, the first thing, as I said, in this process is we have to pre-plan, depending on the project. Here, it's a monastery, but we have to pre-plan because each project has different, requirements. Then we go in the field to deploy our drones or our laser scanners. Perhaps we have to do both. And the output, let's say, the product of this process is many photographs. As you can tell, they are all overlapping. There is a 75–70% overlapping. And from there, we use a specific software, a specialized software. And these days, we use a lot of the MetaShape of Azisoft. And what the software does is basically aligns the photographs. It puts them in the right space, but sometimes it has to throw out some photographs. That's why we need to have many. It just wants to, put the photographs in a certain position so that they are verifying, each photograph verifies the other in some way. And then from there, we can get the structure of the object, right? That, as I said, emerges from the fact that we have several several photographs of the same point, let's say, from different locations in space. From that, we get the point cloud, right? And point cloud and a mesh texture, which are the two ingredients from where we can produce all different types of models, 3D models, beam models, or any type of models that we need. And they are very accurate. They can go up to 1 centimeter of accuracy if that is of interest. We can also have indications of all the materials, etc. Right? So and thirdly, that I must say, this can happen quite fast. We can finish surveying a large project like this one in 1 day or 2, which will take several weeks, perhaps months with the old techniques. I'm sure you are familiar with the point cloud, but a point cloud is a set of points in space. I'm going to just very quickly repeat it because these are the two outputs that we use after that to process further if we need to move to a VR or if we want to move to a beam representation. That is the basis. So the points are represented in space and they have 3 coordinates. And from there, we can, the next step is using again the appropriate software, MetaShape in this case, we can produce a mesh, which is a collection of vertices, edges, and faces that define the shape of the object, right? The last thing that I said, except from the models, and then, as I said, we can further process this mesh or the cloud point to towards different directions. And a third thing that we may need to produce often is the specifications and guidelines. As I said, every project has different requirements, and therefore, sometimes cities ask from us to deliver a protocol to them, the steps that they could follow in the case they want to revisit the process to produce a more updated model. And we usually do that. We produce this set of protocols. And here is a recent example of a work that we did for the mayor of Athens, the municipality of Athens. And up you see is the municipal market of Athens at the center of Athens. And you see a photograph and you see the model at the bottom. And we also deployed the same means to survey, to capture the little open space that is at the front, like a piazza, in front of the building, and the neighborhood, right? Again, on the right, you see a photograph. On the left, you see the model. right? The model gets more and more rich, right? More and more refined. And from this model that you see on the left, we can move to precise beam drawings with all the indications of materials. And that ties really well to what, carbon footprint calculations, requirements, and heat islands for neighborhoods. Here we see the neighborhood of take from the drone. And again, this can happen in very short time. That's the interesting also. We can retrieve this information in a matter of a week. Here is the interior. Interiors are much trickier, especially when you go into a public market and there's very cluttered environment. You see on the left and the right face from the scanning process. This is the result of laser scanning, which is a terrestrial process, and it's extremely accurate. And you see, the indications of the geometry and the materials as well. And the output of this process, on the bottom left, you see the plan of where the blue dots indicate the position of the tool every time we position the laser scanner to have overlapping readings of the space, right? And the laser scanner scans the environment at 360 degrees. And we produce this very detailed, you see on the upper right, model that involves measurements and at the same time materials, indications, texture maps, right, that we can then associate with materials if we like. And that is combined with information from drones and open data if necessary. I'm showing you here something that we did for the medieval castle of Chalki. This is the result. This is a model, right? It's a model. It looks like reality, but it's a model. It's extremely accurate. And it's also an example of, it's not an urban project, of course, but it shows how, beneficial is to use these methods for projects that it would be impossible to capture with the traditional means. This took 2 days to finish. And then after that, having the very refined model, we can move into beam specifications if we want, and indicate the materials and have a very precise, as I said, we can go as close as to 1 centimeter accuracy. So these are the 3 steps that I mentioned: point cloud, mesh, and detailed architectural drawings. From there, we can go as deep as we like in terms of technical detailing and information.
And so we'll move forward here with the embodied carbon footprint and how we can actually apply this information into this process. So what actually embodied carbon footprint is it refers to the greenhouse gas emissions that arise from manufacturing, maintenance, and also the disposal of building materials. And we have done this application, like this methodology already for residential houses. But right now with this methodology that Sotirios showed, we are able to transfer that also to existing buildings, other than the model buildings that we usually do with this building information models, the BIM models, for instance, the Revit. And here on the right, we can see this pie chart, which shows the environmental impact of our approach. And as you can see here, for instance, the concrete is one of the biggest global warming potential matrices that calculate that creates this embodied carbon footprint and the emissions. So, yes, sorry, I had some background noise here. And actually the importance of this approach is that right now we have a methodology, and we need actually to be able to not only capture and calculate this embodied carbon footprint for buildings, but we planned to create, but also for buildings that already exist. And for instance, for so many buildings in Athens, there's like this thought, okay, am I gonna invest into advance this building, remanufacturing? And this kind of computations, this kind of process can help us to define whether a demolition is necessary or whether there are other more environmental friendly approaches that need to be done. Please, if you could move to the next slide. And like I said before, like one of the big problems in the environmental and the city environment is the embodied carbon. But one other very challenging problem is the urban heat island, which is actually a climate phenomenon that results in increased temperature in the city center due to the buildings and the streets and the low vegetation compared to its surroundings, the rural areas where there's more green and the actual temperature of nature. And there are two basic methodologies on how to compute the urban heat island phenomenon. One is based on the air temperature and the other one is based on the land surface temperature. My colleague Jay Crutchen at MIT, he did a correlation between the UTI phenomenon and the urban heat island based on the air temperature, and we did afterwards together also the same correlation with the land surface temperature. And as you can see here, we use for the calculation of the land surface temperature, we use satellite data, as shown here, the area of Greece, and more specifically in this rectangle Athens. And we, in order to separate the rural and the city area, we use OpenStreetMap data to define the city boundaries, and then we define a buffer around this for around 30 kilometers. A main factor in order to compute the land surface temperature is the NVDI, which is a vegetation index, and we use different bands of this satellites information, and more specifically the band 4 and band 5, and these bands have a resolution of 30 meters that are not the best. Like, I mean, before we're talking about centimeters of like accuracy, and now we talk about 30 meters of like distance, but for a bigger city scale, it's a good enough, I would say, for now approach. The way that this is defined is that the NVDI of rural areas are usually below, bigger than 0.2. That means that there's more vegetation, and for the urban areas, it's less. And this is one of the main first like indexes that are needed to calculate the land surface temperature. So, and on this image here on the left, we can see the land surface temperature and actually the UTI phenomenon in the city of Paris. And as you can see here, actually, it's true that due to our calculations, we were able to identify that the city center, where the color is red, has the highest temperature. And as soon as you move to the more rural or suburban areas where more green areas are found, the temperature decreases. And maybe
So-
like, yes, yeah, sorry. So like, this is like one of the aspects that, like what I said before at the beginning, is that right now we need ways to quantify cities, but we also need ways to quantify the environmental impact of things going on within the cities. And some of these approaches and methodologies are able to help us to quantify these aspects.
So I can add here that one of the areas that we can work is microclimate prediction. We were working on a similar project at MIT for producing warnings. In collaboration with the municipality of Boston to issue health warnings for sensitive population groups, depending on the area of their residence, and somehow while taking into account microclimate parameters and prediction. As another thing is, of course, the precise quantification of embodied carbon for existing building stock, using both photogrammetry and open data. And as Tina said, this is very important if we want to have an understanding of how we can develop or redevelop a specific area, a specific building, or a neighborhood. It becomes important. It becomes feasible to inform our process with specific calculations and data with respect to these carbon footprint or heat island, predictions. And finally, fourth step will be to expand this methodology to quantify larger chunks of the city, as the city of Athens wants us to do for various purposes. But the moment you get these models in place, as I said, there are several different paths that you can follow. And I'm sure even the cities right now, they are not aware of the possibilities of these new technological means. And the future is bright in this respect, for cross-disciplinary collaboration among engineers, material scientists, architects, and surveying people across the board. So I think this concludes our presentation, and if we are ready to answer your questions, if you like, if you have some.
Tina, can you hear me?
Now I do.
Oh, yes. Okay.
I assume you were speaking, but
okay, sorry. Well, thank you for your talk, and thank you for bringing the discussion straight on this idea of data acquisition. So there are two things that I want to discuss with you guys, and have your opinion on this. First, you were showing those laser measurements that are like one-time thing, and you deploy the laser and you get whatever nice picture in 3D, very precise with better than 1 meter. Or you have this sensors deployment and networks where the acquisition is like every second for the rest of times. So this is, my discussion is on the sobriety of getting data. I'm telling you that because my experience with at least French cities is they're not ready to be smart. They're not ready to have an acquisition of tons of measurements every second for the rest of times because they don't know what to do with data, right? So what is your stake in there? Are we going to move with this like one shot, the deployment of a sensor, like the laser thing? Or shall we go for more like permanent measurement of cities? What is your stake on this? Tina, Sotirios, tell me.
Yeah, so I might give my opinion on that. So like in most of the engineering processes that for some things, you need very accurate data. And in order to do some calculations and to get the ground truth, you need to have some information in a very high detail. And I think that this approach can give us like this first initial truth, and then hopefully the approach is to be able to define methods to be able to compute like the embodied carbon footprint or any other of these very important topics with other less data intensive methods. But I think that like for getting the first initial good results and to be able to predict what the next results are going to be, I think that it's kind of a very important initial step. That's my take.
If I can give my take, I think first of all, municipalities they start now understanding what they can possibly do with all this data. It's true that data from sensors is quite impersonal. People do not relate very well with that. It's just numbers. For the non-specialists, it's very difficult to communicate, and it's very difficult to imagine where can you go. Well, you have this data, especially if this data keeps updating constantly, and it's the easiest thing these days to implant sensors everywhere, and nobody in the end. No, very difficult. It's very difficult to make sense. As you said, we are not ready for that. At least cities are not ready for that. On the other hand, my experience with models is that 3D models, especially. Despite the fact that there is a whole analytical process behind them, right? And they are very precise. People, officials relate much easier, and also, non-specialists, citizens, people who are involved in the stakeholders that are involved in the decision-making process are much more able to communicate, to understand, to comprehend this type of representation, and that makes, first of all, it makes more possible to open up the discussion. Secondly, the good thing about these models is that before you start, as I said, you have to plan. What are you up to? What are you up to? You have to bring the issue before you get the data, because you can get all different types of data, but you have to have a plan as to what is of interest in its case. And I think that raises the possibility of getting people into this way of thinking. And that's why I do believe, and I saw that with the mayor of Athens, who is not a technical person, but he immediately, he wanted to go ahead and try that and see where can we go. And there are several different ways to move ahead, to go into technical detailing or to go to less, more cultural kind of issues. So, yeah, I guess I believe that both sensor data from sensors and surveying data are going to play a role. There's no, question about that. But the visual aspect of those super accurate models at the moment, I think, resonates better with non-specialists.
Well, thank you for your comments, because I'm sharing my experience with the French cities, and they just don't have neither the capacities to analyze any big data, so they will rely on academics to do so. And second, they don't have they are not going to have a supercomputing facility just to store the data, right? So it's kind of the sobriety into data is, I think, a point to be discussed. Next point I want to discuss with you is the scale. We say all multi-scale, because my own experience tell you, it was 4 months ago, I was attending a satellite conference. It was all about measuring heat island on, temperatures. And I realized that actually the scale, the precision they can get, those guys, I thought they were able to read my newspaper from the sky. That's not true. To have a resolution, you need 3 pixels, right? Each pixel is 50 meters, at least for the European satellite network called Sotirios, is 50 meters. So at most, they have a resolution 150 meters, which is way bigger than the neighborhood, right? Already. So they don't have too much of resolution. What I discovered at the same workshop was this laser thing, where actually this is a program, I think, from the French government, where they are mapping the whole France with the flying planes at 2 kilometer altitude with a laser, and they measure everything, including trees, cars, with a resolution better than 1 meter, better than what, maybe 30 centimeters. So it's very good, except that they are not going to do that every week. So you see, there's this kind of balance between having data not so good in resolution like every day, and doing this laser measurement. So at the end of the day, what we need really to do this urban climate thing is more local data. So we need to equip local areas, not all of them, few of them, the representative one, with some sensors, or have this laser measurement for the heat, because when you do laser, you can also do chemistry, you can do heat, you do infrared. But I think it's better, I mean, this is my point of view, than having those permanent surveys with tons of infrared data that the resolution is not so useful for the climate in cities, because we cannot distinguish better than the scale of the neighborhood. What's your stake, Tina Sotirios?
Should I go?
Yes,
okay. Yes. I can just say very quickly, I think there is a tone of issues that these new technologies open up. You know, there are very social reactions. People are not used to, you know, see planes and especially if you want to do that with the airplane, right? You can do it, as you said, once every few years, but you cannot do it every day for sure, or you cannot do it every month either, not even every year, perhaps. You need, you know, and there are so many administrative obstacles to do that in that manner. Perhaps if you are in a local, you know, collaboration with the mayor for a municipality, I mean, you can always deploy for a certain neighborhood. You can deploy those drones or these laser scanners and get measurements, as you know, technical people used to do these types of surveys all, you know, in the past. It's just a step up, and also, you know, implanting some specific sensors, perhaps it can be useful, but in a very targeted manner, not just everywhere and everything. And yes, I mean, I think that the key issue here is how we get microclimate prediction, neighborhood by neighborhood, in the right scale. Otherwise, we are not going to get too much more than, you know, what we know, which is pretty chaotic at the moment. But I think it becomes important for people to get this, in large cities especially, to get this predictive aspect out of the models that we can deploy right now, and have a better understanding on how the climate conditions appear in a specific chunk of the city, specific section of the city. As I said, there are very many reactions every time we do this. And even in Athens, we had to, like, people don't like to see the drone flying over their heads. I mean, I can tell you that. And Google also has a ton of information, but it's not accurate for this purpose. And then getting a plane that is formally is going to happen through some authority. It's not also extremely easy to achieve.
Yeah, but actually, this is an interesting. I mean, the local data are good and interesting. For instance, what is currently missing out of Google Map or OpenStreetMap? Maybe I'm wrong, but I think at least for the French cities are the heights of buildings. So if you want to model,
Correct.
If you want to model any heat business, is the amount of facades in vis-a-vis. If you don't have the height, you have to assume things, right?
Right,
so
absolutely.
They do have the municipality. That's why it's so important to connect to them, because those guys, they do have the data, except that at least French websites are not well documented. If you compare to the US, in the US, you have every building description with the height, for instance. I mean, everybody at Chicago, at least New York. So that's the thing, is access to data, measuring data, what scale. And so I'm very happy to see that Athens is so enthusiastic with this.
Right.
I can tell you that's not so much the case with French cities.
Perhaps it was an accident, Roland. I don't know. I mean, it was just, it just happened. But you're right about Google. We don't have the heights. There is also a rumor that Google secretly is doing this, is filling in the gaps while we are talking with all this information. But on our side, we just, we just think that it's possible to fill in the missing information and create those more informed models.
Yeah.
So, yes, Tina?
Yeah, maybe my point on that, first regarding the satellite data and all of that, is that like it was one of the basic problems that I saw also while doing this computation. And like this Landsat 8, it's for some reason it has like a 30 meters resolution, but you really don't have a very good accuracy. And if you have like a small park, it won't account for that to compute the temperature well. But the other way how it usually is done, how we usually compute the UHI is like by taking just a few measurements within the city and one at the airport and compare these two values. So I think that transitioning from the air temperature to the land surface temperature, it kind of already gives us a more advanced result compared to how we used to compute the UHI in the past. So that's my point in regard of that. But I'm definitely sure that more information is needed. And I've been having this problem with the heights of the buildings for a long time, because I wanted to do CFD analysis also within the city environment, and it was very difficult to obtain this data. And also last year, the same problem, like from OpenStreetMap, you're able to get a very good, like the footprint of the building, but any other information is not included. I mean, from the OpenStreetMap data, like Google Maps anyways does not give these data for free.
Well, thank you, Tina. Just one thing to add, for instance, yes, this is very important what she said, because what you measure, the surface, as you can see from the sky, is not the heat island effect. This is the energy that's released by facades when exposed to sun overnight. This is not the direct temperature measured by satellite during daytime. That's the conversation I'm having with some cities in France, where they were showing, oh, we're doing this. We do have the data for satellite. The guy was showing me the city of Nantes in a full summer at 1 p.m. Obviously, the temperature of the roof was 50 degrees, but that is not the urban heat island effect. You need to teach those guys what is the physical effect that we're measuring. And again, surface temperatures are not the street temperatures. So, okay, thank you, Tina. Thank you, Sotirios.